Welcome to the CiA webinar, Cane-Based Networking in Agriculture. I'd like to inform you about the usage of cane-based networks in different applications in the field of agriculture. Before we start with a presentation in detail, I will give you a short introduction by myself and of the CiA user organization. My name is Holger Zeltwanger, and I'm an electronic engineer and a technical journalist since more than 50 years. So I'm also the initiator of the non-profit CiA organization, and since its establishment in 1992, I'm a member of the board of directors. In addition, I'm also in some of the standardization bodies active, like ISO, IEC, SIE, DIN, etc. And depending on which behalf I'm talking, I have different hats on my head. Today, I'm speaking on behalf of the Cane Automation Users Group. The CiA Users Group is a non-profit association to German regulations, and its purpose is to foster the image of the cane technology and to provide a path to future cane-based network technologies. So we are mainly focused on developing standards and specifications and recommendations, especially for cane open and also for other standardized cane-based higher layer protocols. We provide technical product and marketing information to the cane community, and we are highly committed to support international standardization. So that is the purpose why we are today talking about cane in agriculture. CiA provides several services, mainly focused on the specifications and standards. And to promote them, we have some tools for that. We are going to trade shows, for example, in this year to the Agritechnica in Hanover, to show what cane is doing in these different applications, as I also will report today. We have also some product guide and publications. We're organizing events like this in webinars, technologies going in much more detail, and also the International Cane Conference, which has been started in 1994 already. We also provide consultancy services and testing services, in particular for cane open-based networks. So let's go into the details. In the first part of my presentation, I will give you some introduction into where cane-based networks are used. This includes a brief history, and then we will discuss also cane in automated livestock, in greenhouses, and where cane is used in deeply embedded networks in this application field. It all started a long time ago, already end of the 80s. DIN, the German standardization body, developed the LBS. This stands for Landwirtschaftliches Bussystem. This means agriculture bus system, and they used a low-speed physical layer. In the early mid of 90s, a German company automating cowsheds, they also used cane-based networks. And in the late mid of 90s, I had several talks to Dutch greenhouse suppliers interested in using cane-based networks because of the reasonable hardware costs, because you know that this is price sensitive, this market. On the bottom, you see a picture from 1987 by Professor Auenhammer. He was the initiator of the LBS, and you see here that they also have already in mind a tractor bus, which is embedded in the tractor, and there is then an integration network connecting tractor and implements. Implements are, so to say, attachments to the tractor, could be on the front or on the rear. And you need for this a connector, and this was specified in DIN 9684. Already in June, a couple of months after cane was introduced, the non-profit LAV, this is Agriculture Machines and Tractors, established a working group, Electronic Interfaces, shared by the professor who has this idea to integrate tractors and implements by means of a communication system. In 1987, this group started the development of the LBS bus system. 1 year later, they decided to use for that purpose CAN, and a low-speed physical layer was taken. In the 90s, the first documents of this DIN 9684 standard was published. Intended was 5 different parts. However, in parallel, the ISO, the International Standardization Body, started to adopt DIN 9684 series in 1995. The first document was released, an ISO standard, ISO 11786, and this was a tractor-mounted sensor interface. This was a dedicated application for the that was what was specified by DIN. After long discussions, and there was a very big conflict between Europe and the United States, they decided to develop a J9039-based multi-part standard, today known as ISO 11783 series, or it is nicknamed ISOBUS. The ISOBUS documents were released step by step, beginning of this century, from 2000 onwards, and the real market penetration started in the mid of the first decade, around 2006 to 2010. In the meantime, standardized conformance testing and Plugfest accompany the usage of ISOBUS connectable tractors and implements. So this is a need to guarantee that products are compatible and interoperable. Nowadays, many of the ISOBUS related documents are pre-developed in the non-profit REF organization and before they are submitted to ISO for international standardization. The benefit is that this association also funded some some experiences before these documents are going into the release process, and then you can prove that these documents or these specifications will be possible to be implemented. REF and CiA have a partnership, so we support them wherever we can. The series of ISO 11783 comprises today 14 parts. Most of these parts are under revision. This is a normal process in ISO, that documents which have some age that they need to be adapted and need to be improved. In particular, the part 3 and part 2 are quite old and they have some weaknesses, and now we are going to improve them. And this is also the case with all the other documents. Some documents are still stable, but most of them are under review. Under review this is done in the ISO TC23. TC23 is Tractors and Machinery for Agriculture and Forestry committee, and we have the subcommittee 19, which is for agriculture electronics, and they're the working group 1, where they deal with all application and data interfaces, and the working group 5, which deals with the communication infrastructure. So this has been restructured to this group to be more efficient. By the way, the part 3, which was historically named data link layer, is now renamed into application layer, transport and network layer, and this is what this document really contains. The data link layer is the CAN data link layer is standardized in ISO 11898-1. The physical layer has some additions to the ISO 11898-2, in particular the connector and some system design aspects. This is also under review. Regarding the part 3, which is the base for all the for the ISOBUS, has some changes in the proposed new edition. So we replaced the default priority by an assigned priority, and the priority levels shall not be changed, adjusted anymore. This was possible in the past. They are fixed now, and this helps to maintain the network stability, for example, for timeouts, even under heavy network load conditions. It happens in the past that there were some timeouts not respected because of the changed priorities. We also have improved the abort handling of the transport protocol, And this helps to ensure that only the intended transport protocol session is terminated. In former times, it was possible that unintended, you also have closed the other sessions. We also have in the new edition allowing to use proprietary messages for data page 2. And this changes the parameter group length limitation so that we can also use the extended transport protocol, which allows much larger data to be transmitted. What is now not more recommended is to use frames with the 11-bit identifier. This was allowed, but we do not recommend it anymore because of some delays of isobus messages. For your background information, frames with 11-bit CAN IDs win bus arbitration against the same which are using 29-bit IDs. So this means proprietary messages could possibly delay isobus messages, and this was not intended. Of course, we need to be backward compatible. So it is still allowed, but we highly recommend not to use any proprietary CAN frames with the 11-bit format. The last thing what has been changed is control function may be responded with a NAC when receiving a PD1 type message, point to point. This allows a producer to stop sending this message to a certain consumer, and this saves bandwidth. Bandwidth was an issue in some applications, in particular when you have multiple implements connected with a high bus load to the tractor. And all these changes will be introduced, and in the moment we are voting on this document, and we will receive perhaps comments, and then we'll have to observe the comments. And I expect that by mid of next year, at least we will have a new edition available. Isobus is well established, not only for tractors and connecting implements, but also in combined harvesters where the internal communication is then using the isobus. One of the real benefits of the isobus is the virtual terminal. This allows that you can have an implement without any terminal, and you're using the terminal, the virtual terminal, which is in the tractor. Very important are the conformance tests to prove that these products are compatible. And in addition, also the plug fests, which takes place biannually, where hundreds of people test their devices on interoperability. This is one of the big advantages, and this is organized normally by the IAF organization. CAN is not only used in tractors and implements. CAN is also used since a long time in livestock applications. You see here a selection of some robots running through the cowsheds, milking machines, dedicated sensors for this application field. So you can detect something in the milk, and all these things are highly automated. One of the company Lely from Netherlands, they are using CAN Open for this purpose, and they have developed or support an open protocol stack approach so that then you can contribute to that, or they can use this protocol stack for the basic communication for CAN-based or CAN Open-based networks. Here you see another example where CAN is used in livestock. This is an application where we control the heating, ventilation, and air conditioning. Of course, we need then also to interconnect those things to smartphones, to the central computer, or to have some SMS and internet access. But this is outside of our scope. We are focusing on the CAN-based communication, and you see that you have here different control systems, and they are connected to the CAN bus, and we have their sensors and actuators, as well as displays and host controllers. There are several companies providing such equipment. However, most of them use proprietary CaN higher layer protocols. So that means the sensors could not be reused by somebody else. You could not combine them. You need to stay with one of the suppliers. So this is a trade-off, and we can't increase the volume for the production, which would keep the cost lower. Heating, ventilation, air conditioning is not only a topic for livestock applications. This is also for greenhouses. You see here another application for similar applications in greenhouses. Heating, ventilation, and air conditioning is not that different from the functionality point of view in livestock and greenhouses. There are some additional things which are needed to be measured, for example, CO2 and other things. Nevertheless, greenhouse automation is using since more than 30 years CaN-based systems. You see also that sometimes we have an Ethernet connection necessary. So this means, as we have seen before, we need a connection to other communication technologies, meaning CaN to Ethernet gateways. On the right-hand side, you see also some dedicated sensors for those applications, as well as vehicles going through the greenhouses. Also, some of the greenhouses are already highly automated. And you see here from the company Faulhaber an application where they handle different plants by means of CaN open controlled actuators, motors in this case. A very challenging application is the fully automated vertical farming, which we see in first systems. So you see here two of them, which are coming from two different parties. And they use CaN-based networks for that. And of course, this vertical farming is inspired by the Babylonian hanging gardens around 2,500 years ago. And in the moment, it's mainly on salad and some other plants, which we can highly automate. And there is workload. There's no the working people are very low on that. Anything is highly automated. I will come to this a little bit later in more detail. So this means we have a lot of embedded and sometimes deeply embedded CaN networks in agriculture applications. And in general, those embedded or deeply embedded networks are specialized computing systems that are integrated into the hardware they control, often with limited resources because they are price sensitive and we have real-time requirements. Sometimes the real-time requirements are soft, like for air conditioning, but for motion control, as you have seen, this is harder real-time then. Typically, those things are based on fixed function processors and peripherals, and this makes them ideal for tasks like sensing, controlling, and processing data in a subsystem. Often, as I said, they use CaN networks. Those embedded systems can comprise hierarchical and non-hierarchical structured subsystems, also based on CaN networks. So this can be very complex at the end. Embedded CaN networks are not visible to the end user, so the farmer does not know that there is CaN internally in the subsystems. And they do not require any configuration by the end user, because the end user, the farmer, is not an expert in CaN. So he is not the system designer, and anything has to be pre-developed and pre-designed by the supplying industry. Typical examples are also in tractor networks, often based on J9039, or in implement networks, sometimes based on CaN open or proprietary higher layer protocols. There are many CaN-based embedded networks in agricultural robots. This is also including in those for livestock and for greenhouses and other front-end agri-food automation systems. Giving you an example on the Itherbus, you see the typical application here, a tractor and an implement. Internally in the tractor, we have a embedded network. and the driver has no idea that there's CAN in connecting the engine and some other devices there. In the implement, you have, perhaps if the implement is complex enough, another in-implement network, also perhaps based on CAN. And we have the integration network, which connects these two subsystems by means of an open network like the isobus. So we have the CAN open network perhaps in the implement. We have a J9039 network in the tractor, and we have the integration network. The challenge is now how we can standardize all those different things and make them interoperable. And this is something what CiA is supporting. Giving you an example for a more complex system like a potato harvester, you see here two different CAN networks in the implement. And this means also, as I said, there are sometimes more than one network involved in the in-implement application. There are also completely other applications which just use an embedded network like these irrigation booms. You see here irrigation booms from different manufacturers. They all use, or many of them are using CAN-based communication for the actuators as well as for the sensors and for the moving of these irrigation booms. Nothing is standardized here. Everyone is developing its own network and its own components. On the other hand, it would be nice, because these are the same sensors and actuators mainly, if this could be provided by, let's say, not individually to each of the OEM, but then for the entire market. In greenhouse, we have also some embedded and deeply embedded networks. You see an example where we have a CAN open communication as well as local CAN networks, and then we have even below that we have then a CAN sync network which uses synchronized communication. So this means we have a lot of different hierarchies of networks in such a greenhouse application. To summarize, there are installed a lot of embedded CAN-based networks in agriculture applications, and many of them still use proprietary high-layer protocols or proprietary CAN open profiles. The open isobus approach is well established in Europe and North America, and we are struggling in the moment to introduce this also for other countries and other regions in the world. CiA staff supports the isobus standardization in ISO TC 23 ST19 working 1 and 5, which makes the basic CAN-related documents. So I'm personally involved in this work. The second part is looking a little bit into the future of CAN in the agri-food industry. So we have seen that we have already some dedicated application in many application fields, use cases, but how this all fit together when we are going to the agri-food industry. I will explain what this is, and then we're looking to what is the role of isobus, how we can control the environment, vertical farming, and livestock automation. First of all, we need to define what is an agri-food system. The Food and Agriculture Organization of the United Nations has defined that agri-food systems is all or relates to all interconnected activities and actors involved in getting food from field to fork, or to spoon, or to the glass. This broad definition encompasses everything from agriculture production and processing to distribution, consumption, and waste management. So this is an overall approach. So we need to integrate at the end a lot of different deeply and embedded systems into one system which is controlled by a management system. It also highlights the critical role of economy, social and environmental factors in shaping how food reaches our plates. So it's not just how we produce things, also what is the consequences for the environmental things and social things, anything. So the production includes classic agriculture as we know it, livestock farming, fisheries, aquaculture, and forestry activities that provide the raw material for food. Post-harvest handling and storage involves activities like cleaning, sorting, drying, and storing agriculture products after harvest. The processing includes transformation from raw agriculture products into food and non-food products, such as milling, canning, freezing, and baking. So this means, what is the intention of such a agri-food system? That you are controlling the entire process from the growing of things up to the processing, and at the end you can protect and observe the entire system, the entire production line. This also includes, and this is important, waste management, because this covers food loss, and we should discuss this, and waste generated at all stages of the system, posing environmental and economic challenges. So this is a very broad approach, and this will be hard to be standardized. Nevertheless, ISO has established a new technical committee 1 year ago, and this committee 347 is going to standardize these agri-food systems. And this is a big picture, data-driven and principled decision-making, multi-objective optimization of agriculture and food systems. And this includes a lot of things. First of all, we have to agree on some semantics. Then we have to provide models, metrics, and data for the agri-food systems, so that we can feed from the embedded networks these agri-food systems, management systems. We can feed them with sensors, and we get then also some commands to fulfill this by our actuators in the deeply embedded networks. Livestock activities are data management is also necessary for greenhouse, controlled environment, and urban farming. What is excluded is the food products. This is managed by the Technical Committee 34, and they make references to that what is developed for the agri-food systems. And also what is excluded is the agriculture electronics, meaning the isobus. But nevertheless, they should cooperate with this organization so that we can feed also from the implements, from the harvesting machines directly into those big picture or data-driven agri-food systems. CiA has established for this reason a liaison to TCA 347, so that we can have access to that data what we have to provide to those management system, and to get the information from those systems into our embedded and deeply embedded networks. So what is we are basically mainly on the front-end networks. So front-end networks typically connect a huge number of sensor and actuators. This is why we are somehow price sensitive. So we have to provide this by means of reasonable prices. In order to achieve those reasonable costs for these sensors and actuators, markets should not be highly fragmented. This means we should, if we have a temperature sensor, it should be applied to different application or an actuator. So this is, we need highly standardized devices on the sensor side, on the actuator side, on the display side, and the controller side. What we need also is a robust and reliable communication, because for reasonable prices, in particular for low and lower middle income countries. So those countries which are not that rich as they were the industrialized, they also need to use such things to participate from the global benefits. And some of these connected devices are used in challenging environments, meaning outdoor. So this has some impacts on the price, and therefore even more, we need high volumes to keep the cost down. And CAN is a quite good candidate for such front-end networks in agri-food systems, as shown historically, but also for the future. CANopen and isobus higher layer protocols in conjunction with CiA profile, respectively, ISO data dictionary specification enable interoperability and partly exchangeability of devices. This is what we need on the level of compatibility and interoperability and partly exchangeability. In order to be future-proofed, those parameters should be developed communication technology independent, and mappings to the desired higher layer protocols would avoid double specifications. If we are using proprietary things, then it comes to the situation that we have to have a lot of gateway technologies involved, which are sometimes costly. Now it's a question how we can come from the islands, which we have already automated, to a system approach. You can think about a top-down or a bottom-up approach. Agri-food systems are highly complex, and we need to integrate several systems with dedicated histories. We can't integrate them that easy because there is already something existing. So if we would going the top-down approach, then this will take a long time before we have all the documents written and we have anything available that we can design a system top-down. But also the bottom-up approach will not work because there is historical, there are already embedded and deeply embedded systems. And to achieve interoperability, we need to have a lot of effort to integrate all these existing systems into an overall agri-food system. So what we need is a double strategy. We need a coordinated and harmonized top-down and bottom-up development. And CiA can support such a strategy with its experience and knowledge in developing application device and interface profiles. And we can do this also bus system independent. These agri-food systems and subsystems related profiles should be communication technology independent to integrate from the bottom-up approach also those which are still proprietary, and CiA can support the mapping of these profiles to standardized CAN-based higher layer protocols such as CANopen or isobus, and we have for both the possibility to do this in the moment for the classic CAN with 11-bit and 29-bit identifiers and data field of 8 byte, but also for CAN-FD with a larger data field up to 64 bytes. This is supported by both higher layer protocols, and in the pipeline there is also CAN-XL, which allows then even payloads up to 2048 bytes, so that we have a easy integration and migration to Ethernet. All this can be done by some standardization activities within CiA, if this comes to the deeply and the embedded networks, and then to the overall approach for the agri-food systems developed by the TC347. What is the future of the isobus? IF, this is the user organization for the agriculture industry, has decided not to migrate isobus to CAN-FD or XL in the moment. For bandwidth demanding applications like cameras, they propose a high-speed, or they develop a high-speed isobus. This is a 1 gigabit Ethernet approach, and this is under development in ISO TC127 Subcommittee 3 Joint Working Group 16. This approach includes a cyber-secure communication, and this is one of the benefits. And the legacy isobus communication can be tunneled and mapped by means of the IEEE 1722 protocol. This protocol is in the moment under review, and CiA supports the revision by means of comments, so that we can then transport J9039 message or isobus messages via Ethernet. If this is, but we think this will take some time. I expect that this will be in the range of 5 to 10 years before we have all the puzzles together, and then this is going to be implemented in real products. So this means the legacy isobus is expected to be used for the next decade or even longer. Therefore, It should be improved regarding functional safety to meet the requirements of the new European machine regulation, and regarding cybersecurity to comply with the requirements of the Cyber Resilience Act, as stated in the EU regulation. All these things are under development, and we should look that this all fits together. This means also then we need to protect by means of functional safety and cybersecurity also the embedded and deeply embedded networks based on proprietary or higher layer protocols. Additionally, this is one of the challenges for the for ISO. The documents of the ISO 11783 series needs to be improved because they are partly hard to read and not easy to understand. We're working on this to integrate this also then together with the requirements from the agri-food systems, so that an implement not only can control the harvesting or the spraying or whatever is the purpose, that also that we can provide this information into the agri-food systems for general management purposes. This is today not possible, but this is something what needs to be done to provide information and to feed the agri-food systems. The IF is also submitting new functions for Isobus, in particular the tractor implement management, TIM. This allows to control the tractor from the implement. To do so, this means there is a cybersecurity necessary. We need to authenticate things, and we should look that anything is available by means of a heartbeat. And this is also part of the international standardization in ISO TC 23 Subcommittee 19 Working Group 1. To show you just what is not yet available 100% perfect, but we have the data dictionary where we can map those parameters to not only to Isobus, we could also map this to other communication systems, but the definition is sometimes not so easy to understand. This needs to be improved, and we need in particular to integrate also those data and parameters which are required by the agri-food systems. They are not yet part of this dictionaries. We will start to improve the data dictionary by mid of this year, and then we need to add step by step those things which coming from the agri-food system applications. Another thing for the future is the vertical farming. I personally think that vertical farming becomes more and more important. We are just in the pioneer state. This is something what is just starting. And the benefits of the vertical farming is that we use the space efficiently. This allows agriculture in urbanized and space-constrained environments, even in big cities, and we need to maximize food production per square meter, per square foot per meter. It's also possible with vertical farming to produce food around the year, and this is very important so that we are not more depending on the weather, and that we can feed the still growing population in the world. We also need low labor costs, and this is possible with those vertical farm automation systems. And then we can reduce the labor cost by about 30% compared to traditional farms. Another thing is the minimization of water usage, because you are now in indoor application, and then you can work on substrates instead of other things, and this is normally you can save a huge number of water. There's some saying that you can grow salads with less than 80% of the water. There's also other benefits, so that you can go in closer to the cities. This reduces the food mile problems and eliminates the need for long distance transportation. The food is more fresh, and you don't waste energy for the transportation. You don't need any chemicals and pesticides. And this is also very interesting for a green production. Livestock automation is already starting. You see here some additional examples for different kind of animals. And also this needs to be harmonized and standardized, the communication, so that we can exchange experiences from one livestock to another livestock, and to improve then the automation and the feeding and all other things, and also the health of the livestock, so that we can at the end control this by artificial intelligence with the support of it. And therefore we need to standardize the data which we can collect for those evaluation systems, and where we can improve the automation and the control algorithms. This is not only true for what is called the livestock automation. We also can do this on ranges. You see here an example from the United States. There's a cowboy. The cowboy is now an autonomous driven vehicle, and he can feed the animals on outdoor, and also it is possible to monitor the herd, the health, takes wildlife and other things. And this vehicle is controlled, embedded by an J939 network. So it's the same like passenger cars or commercial cars, which drives autonomously. And this technology is reused here for a modern cowboy, so to say. And of course, they also can feed then the agri-food system with some information about the health of the animals and what they have feeded and how you can improve that. Controlling the environment is a huge topic, not only for livestock but also for greenhouses. And they have some similarities, in particular when you're looking to the sensors and actuators. This is for heating, ventilation, and air conditioning. And so there are several subsystems, not only the HVAC controllers, but also the automated door and window controllers, the irrigation controllers, and the fertilization controllers. All together, they need to exchange, these subsystems need to exchange data, and this needs to be standardized so that you can buy off the shelf from different suppliers, different subsystems, and integrate them into your agri-food system. When the monitor data should be processed by an optionally AI-based host controller, it needs to be standardized. And this is the purpose of the ISO TC 347, to provide such data so that we can exchange our experiences with AI-based control systems worldwide. To increase the volume of sensors and actuators, as well as controllers, to keep the cost down as much as possible, we need standardized interfaces. And for wired communication, CaN is an appropriate communication technology due to its robustness and reliability, and also for the reasonable prices for which you can buy CaN interfaces, because they are used in high volume in other application fields, in particular in the automotive industry. Interoperability and partly interchangeability can be achieved when using standardized application device and interface profiles. Hopefully they will be then communication technology independent, and then you can map them to different technologies. So CaN is for the wired communication in embedded and deeply embedded networks optimized, but others might be then wireless communication as well as Ethernet-based communication. But all of them should use the same standardized parameters by means of application device and interface profiles. So to summarize, CaN networks are well suited for many front-end networks, deeply or embedded, in agri-food system and subsystems. CiA is committed to support the development of network technology independent profiles for agri-food systems. And CiA is also committed to map network technology independent profiles to CAN Open CC and CAN Open FD as well as other internationally CAN-based higher layer protocols such as Isobus and J939. And we support this also that we can tunnel and map them to, for example, Ethernet or Bluetooth or whatever you have. If you are interested in this entire topic, and this is a huge topic, and you would like to participate in one of the above mentioned topics, please contact CiA office so that we can support you and we can do things together. So this is more or less the end of my presentation. Then I'd like to thank you to participate in this webinar. I hope you have got some ideas, new ideas, how to proceed for the future. And might be we will see us again in one of the or the other standardization body, or you contact CiA with your ideas to standardize things and to do things jointly. And thanks to the CiA staff who made this CiA webinar possible. The next CiA technology is going on the topic deeply embedded CAN open applications on September. This will describe a little bit more in detail how you can use deeply embedded CAN open applications and what are the general approaches. This is not related to agriculture in particular, but in general. But I think also those which have in mind deeply embedded network CAN open networks in agriculture applications may participate in this technology day. Thank you.